All right, so we're back for more. We should be able to finish up all of chapter 20 in this video. Well, we'll make it happen. And so then we'll finally move on to stuff that's a little bit different. So we got two big topics to cover, although I hope you guys understand the point that I've been trying to make all along is you guys already know what I'm about to show you, right? You guys already have the tools there. It's just, now I'm gonna say, can you use these tools to build this house, right? And so we're kind of gonna go through the same thing and just talk a little bit about a couple ideas here and there also, right? So two things that we have to cover is we're gonna talk about amides and we're gonna talk about nitriles, okay? So, and we're gonna just kind of see how to make them and what we can do with them. And so if you've been following through with the other lectures, let's start with the amides discussion. If you've been following through with the other lectures, we got one of the major points out of chapter 20 is that there's an order of reactivity, right? Acyl halides are the most reactive and we can turn those into anything else. And those tend to be downhill reactions. We tend to make more stable carbonyls, all this kind of stuff, right? And then the anhydrides are right below that. So those are two good starting points to make our other carbonyl functional groups. We talked a little bit about esters. We talked a little bit about carboxylic acids. And so now we're gonna finish by kind of talking about amides, right? So amides, we can basically, well, let's see, let's start out with a simple thing, I guess. Whoops, I gotta actually get a pen that I can write with. That would be useful, right? So the best way to make an amide is to start with the acyl halide, right? And then we just add an excess of whatever amine to it, typically, right? So if we just add ammonia and we bubble an excess ammonia through a solution of our acyl halide, we'll go through and we will end up forming our amide, okay? And then we also end up forming the ammonium chloride, okay? So this is why we need to have at least two equivalents of that amine present. Now, I want you guys to go through and do this mechanism, okay? Go back and take a look at the acyl halide video if you don't remember what it is, right? But you guys should be able to do this video, this mechanism here, okay? So that's probably our best way of making amides, although we'll learn another method here in just a minute, right? Because what's the downfall of this? Well, the downfall is, our acyl halides are pretty darn reactive, right? We have amine in there, which is a pretty, I would say it's a pretty strong base, right? It's not going to be all that selective, although acyl halides are very reactive, and so this would likely be a very quick reaction to happen too, although probably not, well, not probably, not going to be faster than if there is some kind of acidic group, right? If there was a carboxylic acid group on our R there, then, right, we would have an acid-base reaction between that amine first, right? So just something to consider. Okay, so now that we made an amide, if we take an amide and we put it under acidic conditions, okay? We put it under acidic conditions. What do we think that's going to turn into? Well, I'll go ahead and give you the answer, and then I'll ask you the same question I always do, okay? Can you guys figure it out? Can you guys pause the video here, okay, and figure out what the mechanism is to get there? It's also in the book, right? But that's not the point, right? I know the answers aren't here, and hopefully you guys have worked through it or thought about it or see if you guys, right? The mechanism for this isn't going to be any different than anything else that we've done, right? Take a look. We're under acidic conditions, and we know that under acidic conditions, the carbonyl oxygen is going to be the one that's protonated first, thereby making the carbonyl carbon more susceptible to nucleophilic attack. We've got water around, which isn't a good nucleophile, but since it is a protonated carbonyl oxygen, the water can come in, we open the door, we close the door, we kick off a good leaving group, and we get on with our lives, is what it is, right? So let's take a look at this here then, right? So for completion's sake, right? Whenever you guys are drawing a mechanism, make sure you show every, right, reaction that takes place, right? Every movement of electrons. That's what a mechanism is for, right, to show everything. Okay, there's that. This is what I was just talking about, protonated carbonyl, carbonyl carbon more susceptible to attack, right? Okay, bring in some water. Open the door. Okay. Every time we open the door, your first question should be, can I close it and kick off a good leaving group? Well, let's see what our leaving groups are. Well, this is a fantastic leaving group. It's called water. Well, that's not going to take us forward in our mechanism, right? So that's not, so we need to turn this into a good leaving group. If I just kick it off now, I kick off N minus, an extremely powerful base. Not going to happen, right? Not going to happen under acidic conditions. So we have to turn this into a good leaving group, and we have to, take care of this here. So we end up doing a proton shuffle here, essentially is what it is. This is going to pick up a proton, this is going to lose a proton. These happen in separate steps, okay? Let me just pause here for a second and show you what I mean, okay? So I'm going to change colors here, and this is a good discussion point. So let's do this. And at the same time, we'll do this. This is green plus, and then, okay. Okay, so this is what we're saying is going to happen, right? Something's going to pluck one of these protons off, and this is going to do an acid-base there reaction to gain a proton, right? This will not happen. This should be two separate steps, okay? And the question is, well, why? I don't want to draw two separate steps. That takes like 4 calories to do. I don't want to do all that. Well, you got to think about, remember, what are you representing? Right? What are you representing when you're drawing a step in a mechanism, right? What you're saying is these molecules are coming together in the right, with the right speed, right? With the right energy, in the right orientation, right? At the right time for this oxygen, that specific lone pair, to grab that hydrogen, right? That causes that acid-base reaction to happen there. Okay, so this all goes back to something that we've discussed before, which is collision theory, right? Things have to come together at the right time, in the right way, at the right space, at the right speed. All this kind of stuff goes together for a reaction to happen. So asking for that to happen with 2 molecules is a pretty big ask. Asking that to happen for 3 molecules is pretty unusual, right? Pretty unusual. And so this can also go back to an idea that we had in general chemistry when we learned about mechanisms in general chemistry with oh gosh, I just forgot the word that I'm trying to say here. Well, that was a lost thought. Good thing it's on video for everyone to see. I'll probably think of it in a minute here. But anyway, we learned about these steps in general chemistry, and that name is eluding me at the moment. But typically, the point being, bringing it back into the context of organic chemistry here, is when we draw mechanisms, we typically only have 2 molecules kind of doing something at the same time. Very rarely do we see all 3 of these, because that would be asking a bit much, right? Now, we're doing chemistry on paper, you say, right? Because, so it doesn't really matter. We can kind of take some of these shortcuts. Well, the point goes back to, right, when you're drawing a mechanism, you're explaining how this works step by step by step, right? These would be 2 elementary steps here, right? These elementary steps in a mechanism. That's what I was thinking about earlier there, right? So this is 1 elementary step, and that's 1 elementary step there, right? So that's kind of the idea here, right? And you'll see it's represented in the book there as 2 separate steps, okay? So just pay attention to that, right? This is one of these tools to keep in mind when you guys are drawing mechanisms, right? Kind of only keep in mind that only really, 2 molecules coming together is reasonable. 3 or more molecules, We'll have to, that might happen under specific conditions though, okay? Anyway, at the end of the day, now we have a good leaving group, now we can close the door, right? Okay, so close the door. Okay, and then finally, oops. Let's bring this guy in because physically they're probably going to be closest, right? And then, that's some NH4+, right? Cool. So we can hydrolyze a amide into a carboxylic acid. Seems reasonable, right? No unusual steps in there, nothing too bad. This is honestly a pretty slow process though, okay? This is not going to be something that's instantaneous, right? Because what do we do when we're going from an amide into a carboxylic acid, right? An acyl halide into amide is a huge hill, right? Right, that's something that everybody looks for to ride their bike down that big hill, right? You go fast and, right? So fun to do, right? An amide, the difference, the energy difference, the hill between a carboxylic acid and amide, it's not that big. It's a big hill you have to climb over for it to go down just a little bit at the other end, not too fun, right? So this is actually a fairly slow process. So honestly, if we wanted to make a carboxylic acid, we might go through a different method to get to a carboxylic acid, although it works, okay? So it is a thing that can happen, right? But why stop at one when we can learn two, right? So the other thought here is, oops. Under basic conditions, right, we will end up making this, right? And then if we come back and we do an acid workup, right, then we would end up at the carboxylic acid, okay? Can you guys do this mechanism? It's also in the book, right? But now what is the difference? We're under basic conditions. It's a very powerful base, a good nucleophile. It can go ahead and attack the carbonyl oxygen, open the door, close the door, kick off the leaving group, right? We're under basic conditions, so we end up with a carboxyl 8, right? And then we'd have to come back with an acid workup later on to turn it into carboxylic acid, okay? So that's going to take you 1, 2, 3 steps. 3 steps, I think, to do? Yeah. So let's work through it real quick. Here we go. Open the door. Okay. Close the door. Kick off a lousy leaving group. Why is it okay to kick off this leaving group here though? Well, we're under basic conditions, so forming another minus is not unusual, right? Whereas before, if you go back to the thought that we had in the previous mechanism, we would be kicking off a minus under acidic conditions. That's not going to happen, right? Minuses and pluses, very rarely do we see those happen. We very rarely see a minus happen under acidic conditions and vice versa also. I'm not saying it doesn't or it can't. I know somebody's furiously typing away at the keyboard right now. That's not what I'm giving you guys general thoughts, right? Things to remember in 2 years when you have to go take your MCATs, right? You're like, what did that guy say? Oh yeah, when under plus conditions, make another plus. When under minus, make another minus, right? Unless you want to just go back and memorize everything 2 years from now. It's a good idea to understand what's going on, to be able to explain what's going on, to think about it, right? Anyway, powerful base, we made an acid, so we end up doing acid base, right? And this will take us to that step right there, right? Got it? Fantastic. Do you think this is a fast, reaction? No, not either, right? amides tend to be pretty stable under acidic and basic conditions. We usually have to heat this up. We usually have to, kind of really punch at this to get it going, right? Now, it's a good thing that that amides aren't susceptible all that much to acidic or basic hydrolysis, right? Because otherwise our proteins would have a big problem, right? There's different parts of your body that are more acidic than others or basic than others, and our proteins are held together with these amide linkages, right? And so it'd probably be a darn bad thing if all of a sudden our proteins just started, denaturing and falling apart because they entered the lungs, and the lungs are a little bit more acidic, right? And then, and then our proteins decay, right? So not a good thing to happen there, okay? So these are pretty slow, but they can work, right? Okay, what else? Well, now that we've covered the basics, and what I mean with the basics is I think for pretty much every carbonyl that we've discussed, we've talked about what happens under acidic and what happens under basic conditions, right? And then there's one other reaction that we've always talked about, or that's always been behind the scenes, and that is our good old buddy LAH, okay? Lithium aluminum hydride. Now, if we do that here, okay, what we end up with is maybe not exactly what you expect. Okay, we end up with an amine. That's pretty darn useful, right? That is pretty darn useful. Remember, oxygen and aluminum are good buddies, right? And so the aluminum in the LAH is going to end up reacting with the oxygen. We end up kicking off an aluminum oxide, which is a very, thermodynamically stable compound, right? It's basically aluminum rust is essentially what happens, right? We talked about that a little bit in another video, right? But we end up kicking off the oxygen and leaving behind the amine. Good stuff, okay? So this is a useful reaction if we want to make a primary amine, or if we want to have some kind of amine with it, right? It doesn't have to be primary. We could have different R groups here. It's not that this reaction is exclusive to amides that have hydrogens on it, okay? Fantastic. All right, so there is that. All right, so the next thing we want to talk about then, right? The next thing we want to talk about is, well, how can we get rid of amides in a different way? And this will lead us into our next idea here. Okay, so thionyl chloride with an amide. Well, where have we seen thionyl chloride kind of used before? Well, we've seen thionyl chloride used in a couple places, right? The first time we ran into thionyl chloride is back in Organic 1, when life was easier and less stressful. Peaceful times, right? Okay, but we learned about it first there when we could take thionyl chloride in the presence of an alcohol, and it would turn it into a halogen, right? It would turn it into either with thionyl chloride, it would turn it into chlorine. With thionyl bromide, it would turn it into a bromide, right? They don't form carbocation intermediates and all this other kind of useful stuff that comes along with it. Good stuff. We learned about thionyl chloride when we were talking about taking carboxylic acids into acyl halides, right? So another extremely useful instance where thionyl chloride can help us out. Now here, thionyl chloride is going to essentially do the same thing, okay? Oops, I added an extra carbon there, right? There it is, okay. So here, perfect, okay? So now thionyl chloride is going to take an amide down into a nitrile. Wow, that's interesting, okay? Take a look at the mechanism. It's on page 936, okay? Page 936. I'm not so interested that you guys memorize this mechanism. Again, they're pretty situational for what happens with thionyl chloride, although a perfectly valid argument would be, well, geez, Dr. H, we've talked about thionyl chloride so much, don't you think I should know it? Well, it's in the book, right? Conceptually, right, the things that go into the thionyl chloride mechanism are the same that we've seen, right? We need to generate a good leaving group, and then it gets kicked off, right? So that's all that really comes from it, okay? But what's useful here is we can turn an amide into a nitrile. So now let's go talk about what we can do with nitriles, okay? Now first off, we've talked about this a little bit, okay? in a previous video, and we're going to do something very unusual now. You guys ready? We're going to talk about what happens when we put a nitrile under acidic conditions. And guess what we're going to do next? We're going to put them under basic conditions. Well, gee, right? You know, how unusual. Okay, so let me give you guys what the product is here. Interesting, right? So if we take a nitrile and hydrolyze it, right, under acidic conditions, we can turn it into an amide. And if we keep going, right, and if we keep going, think about this, right? We just made an amide and it's still under acidic conditions. What could happen in theory? Well, if we keep letting this reaction go, right, we would turn it all the way back into a carboxylic acid. And we typically have to heat that up because what did we just say? An amide to carboxylic acid, right? There's a big hill to climb and it doesn't really go downhill too much though, okay? So, but ignore this for a minute, right? We just did that, you know, what, 2 minutes ago, right? See if you guys can figure out this mechanism here. Now look, listen, okay? What do we have? We've got a carbon that is bound with pi bonds to an electronegative atom. Okay, and we're under acidic conditions. Now think about this. We have a carbon that has pi bonds to an electronegative atom. What happens under acidic conditions? Well, we end up protonating the electronegative atom. What do you think is going to happen here? Okay, the exact same thing. Okay, the exact same thing. We're going to end up protonating that nitrogen first. Why? Well, that makes our carbon more susceptible to nucleophilic attack. Then we swing up the door, right? We have to look at swinging it back down and do this, all the other kind of stuff that comes along with it, okay? Great time to pause right now and see if you guys can come up with a mechanism starting from that point, right? Protonate your nitrogen and then see what happens from there, okay? Cool, let's do it. Okay. Attack at the quote carbonyl carbon, right? So very similar to what we saw previously. Now we got to shuffle some protons around, right? Something's going to come grab one of these and something's going to end up protonating that there, okay? So let's do that. So what have we set up now? All right, well now we have an opportunity to close the door, right? Let's do that. So we close the door. What do we end up with? Cool. There it is. Right, this might be the only odd spot here, right? But remember, the goal is to make a carbon-oxygen double bond again, right? Those are our bonds that we really like. They're good. They're good bonds to make, if that makes sense. Makes sense to me. I don't know. Hopefully, it makes sense to you guys also. All right. Nothing too unusual here, right? We protonate the electronegative atom, we attack at the carbonyl carbon, we shuffle around some protons, we end up closing the door, and then we form our carbonyl at the end. Okay? Yeah, that's it. Not much else to say. All right, let's change colors because we've been using blue a lot. So what's going to happen here? Well, same thing. And then we think about the same situation again, right? We have an amide under basic conditions. We could, in theory, go on to hydrolyze this all the way down to the carboxylic acid, right? But in the meantime, let's just look at this mechanism. Oops, I already got my lights there, right? Okay, okay. Oops, there we go, forgot my minus. Traded one minus for another, made a powerful base. We shuffle some protons around. We're under basic conditions, right? So something's going to come in, deprotonate this. Now we can close the door. And finish up with our acid base. All right. Cool. Similar to what we've seen in the past, right? Got a better nucleophile here. So we start out with attack at the carbonyl, shuffle some protons around, close the door, end up with our product, right? Pretty darn cool. And that's a clue, okay? That's a clue. We have a powerful nucleophile with a nitrile group, okay? So let's think here. Let's use a little bit of red. Oops. So, expanding on this thought here, if we put a Grignard in the presence of a nitrile, so another powerful base, powerful nucleophile, what's going to happen, right? Well, powerful nucleophile, carbonyl carbon, okay? So essentially, just bear with me for a second, right? Essentially, we would end up with this, right? And then that would end up getting hydrolyzed when we come back with our acid workup here, right? Come back with our acid workup. Which means now this is unusual, right? Now we can end up making a ketone. Ooh, that's pretty darn useful for us to make, right? So starting out with a nitrile, we can end up making a ketone if we add a Grignard and then work everything up acidic, right? So this mechanism is back in chapter 19, okay? This is back in chapter 19, we learned about that in there, right? When we talked about shift bases and all that kind of stuff in there, okay? So go check that out. If not, you guys can figure it out, right? We're under acidic conditions, we have a minus, we end up protonating, make a good leaving group, water comes in, all this kind of stuff, right? And we still actually have a carbon which is bound to an electronegative atom under acidic conditions, okay? So you guys know the answer already, okay? Finally, certainly not least, our good old buddy, LAH, coming in clutch to help us make another amine. Cool. What's so different about this? Powerful nucleophile, powerful base, carbonyl carbon, attack here, kick things up, move things around, all that kind of stuff, right? So, and don't forget, we want some kind of aqueous workup. Now, why would we want an aqueous workup? Well, we have to be careful using an aqueous workup here instead of an aqueous acid workup. Well, remember, amines are bases, and if we put them under acidic conditions, they're going to end up getting protonated, right? So we just do a water workup here that's perfectly reasonable for whatever we need to do, okay? Cool, I think that's all I need to cover with you guys for this chapter here. The rest of this chapter is kind of talking to you guys about synthetic strategies. Darn useful to look through. Page 944, right? Page 944 is a very useful resource. It shows about how we can transfer, one functional group into the other and all the conditions and all that kind of stuff that we talked about, right? So here's the bad news. You could skip the last basically 6 lectures and just look at page 944 and there's kind of what you need, although it doesn't explain why things happen and how things happen, right? But it's there for you guys, okay? Awesome. I will see you guys in the next video. We will move on to chapter 21.